So now we're going to get into alcohols. And one of the first things we can say about alcohols, and probably not surprising, is that ethanol was one of the first organic compounds to be, we could say intentionally made or purified. In fact, there's evidence that processes like fermentation go back more than 9,000 years, and distillation, one of the things we did in lab during first semester, one of our techniques that we learned, is a process that's been around for close to 1,000 years. Ethanol itself is really, really easy to make. And we make it by a reaction that we've already learned before. Acid catalyzed hydration of an alkene. And for ethanol, you take ethylene and you heat it up with water and phosphoric acid up to about 250 degrees, and you get a nice high recovery of ethanol. And in fact, this very simple reaction is actually used industrially to make hundreds of thousands, if not millions of gallons of ethanol every year that are used for non-food, non-drinking purposes. Now, the ethanol made in this process is about 95% pure. And it's very difficult to get ethanol purer than that. At 95%, ethanol forms an azeotrope with water, an azeotrope being a substance that's a mixture of liquids, but essentially behaves as if it's a single liquid. And it turns out you can't get, you can continue to distill ethanol and you'll never get it above 95% purity. Only when you distill it from something that will actually pull the water away, and it's most commonly done using benzene. You add a bunch of benzene, the benzene actually pulls the water out. Can you get to 100% or 200 proof ethanol? But at that point, it's certainly not something you'd want to consume, because at that point you've now added benzene to it, and benzene is pretty bad for you. So we're going to start out with some nomenclature. So how do we name alcohols? Well, a lot of what we do with nomenclature of alcohols is exactly the same as we've learned for other functional groups. It's just we have, like always, each time we add a new functional group, we have a slight change to what we do with our nomenclature. And so for alcohols, the key piece of the nomenclature comes right here from the OL. And so we do everything the same that we would. We find our parent alkane here. This is 5 carbons, which means it's pentane. But because it's an alcohol, we get rid of this E and add OL. So this becomes pentanol. Now, we're not quite done there, because just like with alkenes, we have to show where the alcohol is. And so when we're naming an alcohol, we number our chain so that the alcohol gets the lowest possible number. And the alcohol takes priority over any of the other groups that we've learned so far. So it takes priority over any substituents, it also takes priority over alkenes and alkynes. So we can see here the alcohol is on the second carbon, so this becomes 2-pentanol. Or you may recall with alkenes that sometimes we put the number in the middle of the name, and we did that in order so that when we have more complicated groups, like we'll get to in a moment, we know which number corresponds to which group. So in that situation, 2-pentanol becomes pentane 2-ol. Are we done? Not yet. So don't forget, even though we're doing nomenclature of alcohols, stereochemical descriptors such as R and S, or if there was an alkene, E and Z, are just as relevant as they were before. And the carbon here that I've highlighted in green is a chiral center, and so we do have to account for that in its name. The alcohol is first priority, the propyl group to the right is second, the methyl is third, and the hydrogen, which is not drawn in but pointing back already, is fourth priority. We can see our arrow here goes clockwise, and so we have either R2-pentanol or R-pentane 2-ol. Now, what if we have more than one alcohol within the compound? Well, we do the same thing that we did when we had more than one alkene. If ene was our ending for an alkene, 2 alkenes became diene, 3 alkenes were triene. So 2 alcohols would be diol, 3 alcohols, triol, and so on. So we can see this compound is 4 carbons total, so we know that it's butane. We'll number it from left to right. And because there's 2 alcohols, we have to say diol. Now remember, when we named an alcohol on the previous page, we got rid of this E and added OL. When we have a diol, you keep the E. So this becomes butane, and then we put the numbers 2,2-diol. Alright, finally one more example here, and that's what happens if we start to combine functional groups. So now we've got a compound that has both an alkene and an alcohol in it. So we start numbering at this end because that's closer to the alcohol. So we've got pentane, we've got an alcohol at carbon 1, we've got an alkene at carbon 3. So both of these now get inserted into the parent name. And they happen like this. Pentenol. So when we had an pentane without an alkene but with an alcohol, it was pentanol. When we add the alkene in, just like we did before we got to alkenes, we just add that E back in and we get pentenol. If we had an alkyne, then it would be pentinol to show the alkyne. But we also need the numbers. And now for one of the first times we're going to see why those numbers have to be internal. If we just said 1,3-pentenol, then we don't know which number applies to the alkene and which one applies to the alcohol. So instead, we put those numbers in the middle of the name. The alkene is at 3, so 3-ene. The alcohol is at 1, so we get 1-ol. So pent 3-ene 1-ol Maybe doesn't flow as well as it does without the numbers in the middle, but now we know exactly which number corresponds to which functional group. And we're almost done here, but again, and we say this all the time, don't forget your E and Z. And this alkene we can see is E, and so that gives us our full name. So from here you should stop, and there's a series of alcohol nomenclature practice problems. So take a look at those problems, and then in the next video I will go over the solutions.